The last section that we're going to talk about with circles is on locus. Now, locus is the set of all points that satisfy a given condition or set of conditions. We're going to talk about 5 basic locus theorems and possibly combine a few of them together. Copy them down for now. Make sure you're using your protractor to accurately draw everything. The first is the locus of points at a fixed distance d, so d is the distance, from a point P, is a circle with the given point P as its center and d as its radius. So an example of this would be the student radio station has a broadcasting range of 24 miles. Describe the locus of points which represents the outer edge of the broadcasting range. So point P would be the radio station, D would be 24 miles, the range that it broadcasts to would be anything that falls within this circle. So this is the locus, this is the set of points that satisfies this given condition. So in general, a distance from a point, the locus is a circle. The second type of locus, at a fixed distance d from a line L, so we're given L, at a fixed distance d, the locus would be a pair of parallel lines d distance from L on either side. So an example of this would be the locus of points 2 units from the line y equals -1. Well, this is our line, y equals -1. 2 units would be 2 up and 2 down. So the locus of points would be y equals 1 and y equals -3. Now you can do locus using dashed lines, that's fine as well, but in general we'll know what you're looking for. The locus of points equidistant from 2 points, P and Q, is the perpendicular bisector of the line segment determined by the 2 points. So this is where use of our compass comes in, because we need to, if we're given 2 points, draw a line that's connecting them and construct the perpendicular bisector of that line. So an example would be there are 2 buoys in a lake, so we have buoy 1 here and buoy 2 here. A scuba diver swims so that he is always equidistant from both buoys. Well, that equidistant line is the perpendicular bisector of the line that connects the 2 buoys, so this dashed line. So his path would be a straight line, which is at any point equidistant from both buoys because it's the perpendicular bisector. So think back to isosceles triangles. We know that equidistant on both sides means that this is the perpendicular bisector of the base. The fourth type of locus are points equidistant from 2 parallel lines. So you're given L1 and L2. This line here, this red dashed line here, would be the locus of points that satisfies this given information. So an example would be the equation of the locus of points equidistant from y equals -2 and y equals -3. So these 2 pinkish purple lines are what we're given. The locus given these lines would be one line equidistant between them, and this line here would be y equals 1/2. So in this case, equidistant between 2 lines, find the average between 2 lines. So these 2 lines are 5 units apart, so you go halfway, you go 2.5 units, and that's where you draw the line. The last basic type of locus are the locus of points equidistant from 2 intersecting lines. So let's say we have L1 and L2. The locus would be a pair of bisectors that bisect the angles. So both of these lines represent the locus and they bisect the angles. You usually see this one on coordinate planes, though we do know how to construct angle bisectors, so we can do it that way as well. We'd have to bisect this angle and bisect this angle to construct our 2 lines that represent our locus. So an example would be, what is the equation of the locus of points equidistant from the x-axis and the y-axis? So x-axis and y-axis are in blue. So we're going to draw the 2 lines y equals x and y equals -x because those perfectly bisect the angles formed by the y-axis and the x-axis. Make sure you have all of the examples copied down for each type of basic locus. The last type of locus that we're going to talk about, it's kind of a combination of the two. Let's say it says the locus of points 1 unit from AB. Normally this is going to mean that they're going to give it to you on a coordinate plane, but you may see something where they tell you this is representing 1 unit. So I've set my compass so that it matches up to this measurement. So 1 unit from AB means not only is it 1 unit from B, from point B, which we know is the circle, but it's also 1 unit from A, and in addition to that, it's 1 unit from the line. So this measure is our distance. It's 1 unit from that line. So it's going to also be from here to here and from here to here. So you can see that this is an oval shape. So when you have the locus of points 1 unit from AB, it's 1 unit in every direction. So if we just were given the line, then the locus would be a parallel line on either side. But if it's 1 unit from AB, it's this oval shape that goes around the whole thing. So just to discover a probable locus, first we're going to make a diagram of what's given. It will either tell you to sketch it, to use your compass, or to do it on a coordinate plane, in which case use your compass as well. You locate one point that meets the given condition which needs to be satisfied, and then locate several other points that satisfy the given condition. They should be close together to develop the shape or the nature of the locus. Use the points to draw a line or a smooth curve that appears to be the locus, and then describe in words the geometric figure that appears to be the locus. Now, compound locus is taking those basic loci and putting them together. So a compound locus problem involves 2 or possibly more locus conditions occurring at the same time. The different conditions in a compound locus problem are generally separated by the word and or the words and also. It's usually going to be a treasure problem. That's the best representation. So a treasure is buried in your backyard. The picture below shows your backyard, which contains a stump, a teepee, and a tree. So we have the teepee, the stump, and the tree. The teepee is 8 feet from the stump and 18 feet from the tree. So the teepee is 8 feet from the stump, so I labeled that 8 feet, and 18 feet from the tree. The treasure is equidistant from the teepee and the tree. So equidistant from the teepee and the tree, so equidistant between 2 points is going to be that perpendicular bisector. And also 6 feet from the stump. 6 feet, a fixed distance from 1 point, is a circle. Locate all possible points of the buried treasure. So what you do first is the perpendicular bisector of the points from tree to TB. So we're going to take, and I already have most of it drawn here, but we're going to go from the tree to the TP and do the perpendicular bisector. We want to go more than 75% of the way. We're going to construct our arc here. We're going to do the same measure arc in the other direction. My compass, do the same measure arc in the other direction, and you can see that this is where I got my perpendicular bisector from. Then we're going to go 6 feet from the stump. Now this is approximate because obviously it's not drawn to scale. This is approximate, but if it's 6 feet from the stump, that means that it's more than halfway, because this would be about 4 feet. That's halfway because this whole measure is 8 feet. So you just want to approximate it so that it's more than halfway, and that's where we draw our circle. Now where the 2 locus intersect is your solution. So I marked those with X's here and here. Make sure you extend all of your lines. but our solutions, all possible points for the buried treasure, are where the two loci intersect, so these green X's, and they're normally represented by X's. Here we have an example on a coordinate plane, so make sure it is on graph paper. Part A asks you to draw the locus of points equidistant from the 2 points, 4, 1 and 4, 5. Equidistant from 2 points is the perpendicular bisector, so keep that in mind. So we plot our points at 4, 1 and 4, 5. We connect them into a line. Now, perpendicular to a vertical line is a horizontal line, and it's a perpendicular bisector, so halfway would be here. So y equals 3 is our solution to this given statement. Part B asks you to draw the locus of all points equidistant from the points 3, 2 and negative 4, 2. So we plot 3, 2 and negative 4, 2. Again, equidistant from 2 points is the perpendicular bisector. So we go halfway, which is to negative 1/2. And again, perpendicular to a horizontal line is a vertical line. We plot our x equals negative 1/2. Part C asks to find the number of points that satisfy both conditions stated in A and B and give the coordinates of each point found. So we extended this line, the green lines are our loci. Where they intersect is at this point, so this is the solution to the given conditions. Both part A and B require a perpendicular bisector of the segment joining the 2 points as the locus. In part A, we get y equals 3, and in part B, x equals negative 1/2. So where they intersect is going to be negative 1/2 and positive 3. Now here, part A is asking us to draw the locus of points 3 units from the y-axis and write the equation for this locus. So 3 units from the y-axis, 3 units from a line, is 2 lines parallel to it. So x equals negative 3 and x equals positive 3. Part B asks us to draw the locus of points 4 units from the origin and write the equation for this locus. So the origin is here, 4 units from a point is a circle. So we count up 4 for the radius and we use our compass to draw our circle. We know that a circle has to be in the format x minus h squared plus y minus k squared equals r squared. The center is 0, 0. The radius is 4 units, so here we have our solution for part B. How many points satisfy both conditions stated in part A and B? That would be 4 points, and you can see them marked here in green. So this just explains all of the steps that we've taken, and the points are marked with a green X. Our next example, determine the points on the plane that are equidistant from the points A, B, and C. So our first step would be to plot points A, B, and C. So we have our A, we have our B, we have our C. So equidistant from 2 points, we know is going to be the perpendicular bisector. So we need equidistant from all 3 points. Well, we know that these 3 points are forming a triangle. Equidistant from all 3 points are the perpendicular bisectors of each segment, and we know from what we know about a triangle that they have to all meet at the same point. So we really only have to find 2 perpendicular bisectors. So what we need to do is find the equation or the slope of AB so that we can find the perpendicular slope that we need for our new line for our locus. So we need the midpoint of each line. So for A and B, 2 plus 4 divided by 2 and 4 plus 6 divided by 2 gives us that the midpoint is 3, 5. And then we're going to find the slope, and we get that the slope of AB is negative 1. So the slope of our new equation that's going to be perpendicular to it is going to be positive 1. So we plot that line, and then we come up with the equation for it. We can see that its y-intercept is 2. You can also solve that algebraically, or you can just solve it graphically. For the other, BC, we're going to also find the midpoint, and we get that it's 6, 5. We find the slope, and we get that it's 1/2, so the slope of our locus needs to be negative 2. We plug in the point that we need, and we get the equation of our new line. Once we have the 2 equations of our loci, we can see where they intersect. This is the point that is equidistant from all of the points here. And we know that point is the circumcenter from our work with triangles.